I'm going to start this video by mentioning a couple of propositions that were proven in Chapter 3, where you can prove them in pretty much exactly the same way. Chapter 3, remember, is Riemann integration in one dimension. So here are four propositions that you can prove that are true in higher dimensions that you prove exactly the way you do in lower dimensions. So if you want to see the proof, you go back to chapter 3, and everywhere you see a partition, you replace it by a rectangular cover. So throughout this section, we are going to let X be a bounded subset of Rp, and F be a bounded function defined on X. And then we have that F is integrable, or Riemann integrable, on X if and only if for all positive numbers epsilon, there is a rectangular cover P of X with the upper and lower Darboux sums of F over that cover. The upper sum is always bigger, the lower sum is always smaller, but it's integrable if you can get them as close as you like. Next proposition. We have that. Let's let P be a rectangular cover of X. Then F is integrable on X if and only if F is integrable on the set X intersect R for all R in our rectangular cover. And if either of these are true, then the integral of F is the sum of the integrals. The integral over all of X is the sum of the integral over all of the pieces. Third proposition I'd like to write down is that if G is another bounded function from X to R, and F is less than or equal to G, that is, F of X is less than or equal to G of X for all X in our domain, and F and G are both integrable, then the integral of f is less than or equal to the integral of g. One last proposition, this is the linearity proposition, and then we will move on to things that are more interesting, that is more complicated in multiple dimensions. If alpha and beta are real numbers, and f and g are two functions from our domain x to r, and they are both integrable. Integrable we're taking to imply to mean as part of the definition bounded. Then the function alpha f plus beta g is integrable. And you've got the formula that you think you ought to have, the integral over x of the function alpha f plus beta g. dv is alpha times the integral of f plus beta times the integral of g. Now let's move on to the bit where things are more interesting, or at least weirder in higher dimensions than in lower dimensions. In one dimension, remember, all connected sets are intervals. So if you want to be able to integrate functions on connected sets, well, just being able to integrate functions on intervals in one dimension is good enough. But there are all kinds of really weird sets, even in 2 or 3 dimensions, that you might potentially want to integrate over various bounded regions, and you can't. So let's write down a definition. This is roughly definition 7.2.8. And I think I'll also put definition 7.2.19 in. I'm doing things a little bit differently from your book, partly because we don't have that many lectures left in the semester, partly because it just works better for me. So let's let X be a bounded subset of Rp. And then the second simplest function you can think of is the constant function, the function that's 1 everywhere. The simplest function is the function that's 0 everywhere, and that's integrable on any set you care to name. But the function that's 1 everywhere is not. Then, if 1 is Riemann integrable on X, then we call X is a Jordan domain. And we write that the volume of X, V of X, is just the integral of 1 over X. The easiest example I can think of a non-Jordan set is actually one-dimensional. It's the rational numbers. I would like this to be bounded, so let's intersect it with the interval from 0 to 1. And then let's let P be a rectangular cover, meaning a cover of closed intervals of X. And then that means P is a collection of finitely many closed intervals. So its union, the union of those rectangles is a closed set. So the closure of X, which is the entire interval from 0 to 1, any irrational between 0 and 1, you can write it as a limit of a sequence of rationals. Is contained in the union of those rectangles. And I hope it's clear to all of you that if you union up finitely many rectangles, finitely many intervals, and get a bigger interval if the intervals are non-overlapping, that means that the length of their union can't be any less than the sum of the lengths of the little intervals. That is, if you can draw a nice bounded interval like that, and then if you cover it with finitely many other intervals, then the length of the interval you started with is at most the sum of the lengths of the smaller intervals. So volume of 0, 1 less than or equal to the volume of your rectangles R. I'm going to throw in the additional restriction that all the rectangles have to actually intersect X. This is not a very restrictive restriction. You just start with P and throw out all the rectangles that don't intersect X. You've still got all enough rectangles to cover it. And that means that we can turn this sum. We can require that R intersect X not equal to empty set. And then if you remember, because 1 is a non-negative function, this is a very nice formula. This is, we can go ahead and multiply by the supremum over R intersect X of our function, which is just 1. We're multiplying by the supremum of 1, which is just 1, which is now the upper sum of 1 over our rectangular cover P. And now, but lower sum of 1 over our rectangular cover P. This is the sum over all rectangles in P that are subsets of X. There aren't any rectangles that are subsets of X. Every rectangle, every non-trivial rectangle, and we can throw away the trivial rectangles, has at least one irrational in it. So our lower sum equals 0. So the upper sums are all at least 1. The lower sums are all exactly 0. So 1 is not integrable. And on your homework, you will come up with another example of a non-Jordan set of, in fact, a connected set that nonetheless is not Jordan. Again, in one dimension, you can get a pretty reasonable theory of integration just integrating over intervals. But in higher dimension, we're going to want to be able to integrate over all kinds of things, over rectangles, over triangles, over balls, over all kinds of sets. So we're going to need some sort of criterion for what kind of set is reasonable and what is not. And this Jordan set criterion is a pretty good one. I would also like to note that this function, that we saw last semester. It's a function defined on the rationals. F of n over d is 1 over the denominator if the fraction is in lowest terms. You may remember the graph of this thing looks something like this. It's 1 at all the integers. It's 1/2 at 1/2. It's a quarter at 1/4 3/4. It's a third at 1/3 and 2/3. Fifth, and then 5/6, and so on. You get lots of these points going downwards. You may remember this from last semester. And this function, I'll ask you to take my word for it, then f is integrable on our set X. It has integral 0 as it happens. Let's say a little bit more about what a Jordan set looks like. So let's recall, if P is a rectangular cover of X, then the upper Darboux sum of our function 1 over P, that's the sum over the rectangles in P that intersect with X. Their intersection with X is not empty. The volume of that rectangle, and then I have to multiply this by the supremum of the function 1. The supremum of the function 1 is 1, and the lower Darboux sum is just the sum of all the rectangles contained in X. So let me draw you the picture of this. Let's say X is this circle here, and our cover is something like this. We'll take this square inside it. Maybe we'll throw in a couple of other rectangles contained entirely in the set. And then we'll patch it up with some other with enough other rectangles to cover all of the set. And then the lower sum is the volume of this region. All the yellow rectangles put together. And the upper sum is you have to add in all these red rectangles. So by proposition 7.2.4, X is Jordan if and only if for all positive numbers epsilon, there is a rectangular cover P of X with the red rectangles sum over the rectangles that intersect X but are not contained in X, their volume has to be less than epsilon. Now let's discuss some Jordan sets that we can recognize. So first off, all rectangles are Jordan sets. And the proof of this is pretty straightforward. Let R be a rectangle. And then the set containing R is a rectangular cover. And the upper sum of F over that particular rectangular cover is just the volume of R, sorry, the upper sum of 1 over that rectangular cover is just the volume of R, is just the lower sum of 1 over that rectangular cover, because the one rectangle in it is contained in our set, is certainly contained in itself, and it also is the only rectangle in the cover, so it's the only rectangle in the cover that intersects itself. And you can look at any of several propositions we've proven before to see that if you've got a rectangular cover where the upper and lower sum are the same, then the function must be integrable. Here's something a little bit more interesting. Let's let y be a Jordan set in Rp minus 1. And let's specify this has to be a compact Jordan set. And then we'll let f and g be functions from y to the real numbers, be continuous. And because y is a compact Jordan set, we've got all our nice results for continuous functions on compact sets. F and g have to be bounded and uniformly continuous, and so on. And then let's let X be the set of all points yt, such that y is in our original Jordan set of smaller direction, and then t is between g of y and f of y. And the conclusion is that then X is also Jordan. And here is a picture of what's going on. So if our region Y is a Jordan set, for example, if it's an interval in R1 or a rectangle in R2, and then we've got our function G and our function F, then our set X is this entire thing. Let us prove this. So by the extreme value theorem, since y is compact, f and g are continuous, f minus g must be continuous. We can say that the supremum over y, the biggest f minus g ever gets, that is finite. And because I would really like this to be 1, let's take whichever is bigger, that supremum, or 1. And therefore, by our proposition for rectangular covers and integrability, and because Y is a Jordan set, there is a rectangular cover P of Y. This is a rectangular cover in dimension P minus 1, such that so Jordan set means 1 is integrable, so the upper sum of 1 over our set P minus the lower sum of 1 over our set P. I can make that as small as I want. Let's go ahead and pick a positive number epsilon at the start of this proof. This is less than epsilon over 2 times m, and I wanted m to be positive, so I could just divide by 2m and not have to worry about it. Now apply compactness again. F and G are uniformly continuous. They are continuous on a compact set, so by a theorem from section 5.5, they are uniformly continuous. And that means that there exists a delta positive number delta such that if x and y are both in the domain y, and the distance from x to y, which we remember we write as norm x minus y, is less than delta, then f of x minus f of y is less than epsilon over 4. Let's call, and we'll see why I want to have the upper sum of 1 over p, which is some finite real number. Why don't I add 1? And g of x minus g of y is less than the same quantity. And because f and g are both continuous, I can find a delta 1 that works for f, a delta 2 that works for y, and just let delta be the smaller of the two. So I can find a delta that works for both of them. Now we can go ahead. Now we would like our rectangles to be small enough compared to this delta. So remember, if you've got a rectangular cover, you can always chop the rectangles up. So we're going to let p twiddle be a refinement of p, which you can get by chopping the rectangles into smaller pieces, such that if r is in p twiddle, then the diameter of r has to be less than delta. So any 2 points in r are within delta of each other. And we might as well insist that this is a non-trivial cover. That is, there aren't any superfluous rectangles that don't actually hit y anywhere. I think I'd probably better draw another picture of what's going on. Here are my coordinate axes. It's two-dimensional, so we're still going to let y be an interval. And then here is our G, here is our F. Then what we do is we break y up. Let me remind you that in higher dimensions, we might be left with some little leftover pieces. And then we remember, or we can refine our cover. We can break it up even further into little small pieces, into smaller pieces. So that F and G are close enough to be are continuous, don't change a lot on there. Here is what we're going to do. We're going to take these sort of prisms, that is tall rectangles, whose base is one of the rectangles that's covering y, and whose height is one of the rectangles and whose height, well, we'll see. What we're going to do is we're going to slice at the highest and lowest that F and G get, respectively, in each of these rectangles. Now, we're going to need some notation. Let's let P1, that's the set of all the rectangles in our refinement P-twiddle, such that the supremum over our rectangle, well, I have to intersect it with y and get a g that is less than or equal to the infimum of F. And we'll let P2 be everything else. That's all the rectangles, such that the supremum of G is bigger than the infimum of F. And so now we're going to come up with a rectangular cover of X, which, as you recall, is the region above G and below F. So it's the region in here. And our cover will actually be broken into 4 pieces. So let's let Q1, this is a cover of X, so it's rectangles in P dimensions. So we start with a rectangle with 1 fewer dimension, a rectangle in our P1, and then we take the Cartesian product with an interval. And we're going to say that R has to be in P1, which means that our supremum is less than or equal to our infimum. So this, well, it might be one of those intervals with only 1 point in it, but it's not going to be nothing. And if we go back to our picture, Q1 is these 3 rectangles here. Now we're going to let Q2 be all the rectangles whose base is in P2. So we'll make this the infimum So these rectangles, remember, they're coming from the rectangles where G and F overlap, where G at some point is bigger than F. So that would be in this picture just this rectangle. And now we've still got some leftover stuff. So we'll let that be Q3 and Q4. And we're going to allow ourselves rectangles with zero volume, just on the off chance that F or G happens to be, say, constant on one of these rectangles. And then Q3 and Q4, they're giving us these rectangles here. And then we've got some it looks like we've got some leftover rectangles here and here, but you'll notice that X doesn't hit those rectangles. So let's it'll prove rigorously that this is in fact a cover. So we're going to let Q be all of these rectangles put together. And then if A and B are in Q, if they overlap, then A is some rectangle cross some interval, B is some other rectangle cross some other interval, and R and S must overlap. So R equals S, because these rectangles are coming from our cover P twiddle of Y. That's a rectangular cover, so it's non-overlapping rectangles. And we must have that the interiors overlap, and the only way that can work, well, in Q2 there's only an interval for each R, and Q1, Q3, Q4, they stack on top of each other. So if you look at it, you must have that our intervals are the same. So the only way you can get rectangles in Q that overlap is if they're the same rectangle. So the rectangles in Q do not overlap. And now we claim this is a rectangular cover of X. So if the point YT is in X, then Y is in some rectangle some rectangle in our cover. And then we have that g of y is less than or equal to t is less than or equal to f of y, which is less than or equal to the supremum of f, and our g of y is greater than or equal to the infimum of g. So x, y, it must be in one of these rectangles. Sorry, yt is in one of these rectangles cross one of these intervals that shows up in our cover Q. So Q is a rectangular cover of X. And now let's think about the upper and lower Darbousums of, well, we're showing it's a Jordan domain, so we want you just use the function 1. The upper sum that's just the sum over all the rectangles in Q, the volume of S. And now breaking this up, we can write this as the sum over the cubes in our first set, Q1, volume of S. And then for Q2, I'm going to write this as the sum of all rectangles in P2. And then the volume of those rectangles, that's the volume of R times the supremum of F minus the infimum over G. And then for Q3 and Q4, I will go ahead and just put those two together. So there's the bit from Q1, and here's the contribution from Q2. Now, the difference between the supremum and the infimum of F on R, that's at most, what did we say? It was epsilon over 4 times the upper sum of 1. And the same thing is true for G. So this upper sum is at most, we'll keep the sum over Q1. That's going to hang out. And then all the other pieces we can turn into sum over R in a p-twiddle, volume of R. And then to this piece, we are going to just add a supremum of G minus an infimum of F. And if you're in P2, that is the supremum of G is bigger than the infimum of F, so we're adding something positive. So I can go ahead and do that at a cost of making this bigger, and that's fine. And then now we've got suprema minus infima. And then when we simplify this, because p-twiddle is a refinement of P, we just get epsilon over 2 and then the upper sum of 1 over p twiddle divided by the upper sum of 1 over p plus 1 because I wanted to be very sure I wasn't dividing by 0. Now let's move to the lower sum. This is the sum over all rectangles in Q that are contained in our set X. So certainly, if I just take rectangles in Q1, certainly not going to get any bigger. In fact, I won't get any smaller. You can probably convince yourself that I won't get any smaller, but right? So we can write this as the sum. So we can write this as the sum over all S in Q1 V of S, that piece that we've got showing up here in our upper sum. And then we subtract off all the volume of all the cubes that are not contained in X. But the only way a rectangle in Q1 can be not contained in X is a closed set at notice. Is if it's a rectangle, if our base rectangle is not a subset of Y. And then what's the height of the rectangle? I don't know what the height of the rectangle is, but it's at most M. M, remember we said, was the biggest F minus G gets. And therefore, this is at most minus, if you think through it, the rectangles in P twiddle that are not contained in Y, that's just the upper sum of upper and lower sums of 1 over P twiddle. And so that's greater than this sum minus another epsilon over 2. So the upper sum minus the lower sum is less than epsilon. And so 1 is integrable, so X is a Jordan domain.